If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. So in our previous tutorial, we started talking about the momentum-based gradient descent, and we saw its advantages. For example, it's a lot faster compared to the classic gradient descent. We also did a comparison between the mini-batch gradient descent, momentum-based gradient descent, and Nesterov Accelerated Gradient Descent, which essentially overcomes some of the opportunities with momentum-based gradient descent. And we concluded our video with the thought that what if we try to change the learning rate as well? Because all the examples covered in the previous tutorial involved a constant learning rate. We didn't change that. So in this tutorial, we begin to talk about the algorithms which promote adaptive learning rate. And one such algorithm is adaptive gradient algorithm. But let's first understand, why do we need to change the learning rate? Why it should vary or adapt as per the data. So let's take a simple example. Let's say we have a data in which we have two features. One is the practice time of the athletes in minutes. Now, if you see, this practice time feature is something that varies a lot, contains a lot of values, and it has some or the other value to offer for every single cell. Such features are called dense features because they have some information and they continuously vary. On the other hand, we have this feature called injury, and of course, not every athlete gets injured every other day. They may practice every day, but they may not necessarily get injured. So obviously, this feature would tend to have more zeros, which means no injury compared to the ones. Such features, which rarely vary, which majority of the times continue to be zeros, are known as sparse features. Now, it is not that the sparse features are less important, because if an injury is recorded, it could be something really serious. But it so happens, while learning, that for the dense features, the gradients are updated very frequently. The neural networks tend to learn them very frequently because they offer a variety to learn. On the other hand, these sparse features, which tend to have more or less the same kind of values for majority of the instances, offer less variety, and that's why their gradients are updated infrequently. This could lead to scenarios where the gradients progress more in the direction of the dense features compared to the sparse features, and that will be a bad idea. So to overcome this opportunity, the adaptive learning rates were introduced. Let's talk about the adaptive gradient algorithm, and we'll see the equations. So we saw the idea of accumulating history when we talked about momentum. But when we talk about adaptive gradient algorithm, it accumulates the squared gradient. You can see this equation where this term gt is something that stores the sum of squared gradients for each parameter up to time t. The parameter update rule in this case is somewhat modified. So far we were saying theta t plus 1 would be equal to theta t minus learning rate times the gradient at that point. But now we are saying we will be dividing the learning rate by the square root of these summed up gradients. And we also add a small constant epsilon here to ensure that we don't end up dividing by 0, because at the initial stages, we generally would have not accumulated gradients. So we don't want to be dividing by 0 to begin with. It will make the learning rate infinity. So if you see, this is a factor which kind of does the adjustment. For a dense feature, these updates will be frequent, and hence the learning rate would come under control, because if the denominator increases, the overall learning rate would reduce. The problem was that for the dense features, the learning was much faster and more frequent. On the other hand, for the sparse features, where we know the accumulated gradient value is much smaller, you can see the learning rate effectively would be much higher, because the denominator is less, the overall value is going to be high. So this is the sense of adaptive gradients. Let's see this a little more visually, and that'll give you more confidence. So this kind of nicely puts a comparison between different approaches that we have seen so far. Imagine this circle here, the black circle is the starting point, and somewhere at the center of this circle here is where we have the optimal point where we want to converge. If you see the classic algorithms like the mini batch gradient descent in this red color, the momentum-based gradient descent in this green color, and the Nesterov Accelerated Gradient in this blue color, all these tend to make a lot of progress in the direction of the dense features. That's the x-axis. You see, majority of the initial updates are parallel to the x-axis, very less movement with respect to the sparse features. But as you know, if this is the starting point and we need to converge somewhere here, I think we are going in a different direction altogether to begin with to finally converge here. Why can't we start straight in this direction and make some progress? Now, you might be noticing this line here, which represents Adagrad, is actually not able to make it to the center of it. That's somewhat a drawback as well. But the strength is, at least, that starts in the right direction. Why it doesn't converge to the optimal solution at times is because of the initial frequent updates for the dense features. So by the time it's kind of reaching the optimal solution, the gradient kind of dies down for the dense features. You can see it made the progress initially, but there's a point beyond which it doesn't seem to be making any progress in the direction of the dense features. It's making the progress in the direction of the sparse features. And this is an opportunity. While the adaptive gradient algorithm picks up a good start, it may not be able to converge to the optimal solution. It may come very close to the optimal solution, but not necessarily converge to the optimal solution because the gradients for the dense features might almost die. So it does solve some problem, but doesn't solve it completely, you can say. Having said that, it's still a popular gradient descent algorithm, and in some data sets, it will work great for us. So to overcome this opportunity of adaptive gradient, the root mean square propagation approach was introduced. And here I'll also be explaining the idea of exponentially weighted gradients. So in case of RMSprop, if you see, it's very similar. The notation might look a little different, but we are essentially trying to strike a balance between the gradient that has been accumulated up to time step t-1 and the gradient at the current time step. So beta is a decay rate, which will be between 0 and 1, typically 0.9. And this 1 minus beta, you can imagine if this is 0.9, this is going to be 0.1. So it's trying to strike a balance between the historically accumulated gradients as well as the gradient at the current point. This notation E g squared t essentially is the representation of the exponentially weighted moving average of the squared gradients. If you see in case of Adagrad, we did not have this beta. We were just simply adding up all the gradients. But in case of RMSprop, we are giving a weightage to the historical gradients and weightage to the gradient at the current point. The parameter update rule is very similar. It's theta t minus eta divided by. So the denominator here is the exponentially weighted moving average of the squared gradients. And this is a small value epsilon, which ensures that we don't end up dividing by 0. Let's work out these equations a little better. So this is the equation we saw on the previous slide for the update. And this was the equation for the exponentially weighted moving of the squared gradients. Let's say we make these symbols somewhat simple. So let's say we introduce this Eg squared at time step t as Vt, trying to simplify the notation because we'll be writing a lot of equations, right? So let's understand how does this equation work. If you've just replaced these values here, how would the equation look like? So at the time step 1, we'll be looking at a balance between the accumulated squared gradients up to time step 0 plus 1 minus beta, the gradient at the time step 1 squared. So the gradient at the current time step plus the historically accumulated gradient, we are trying to do a weighted moving average between them. Likewise, V2 would be using beta V1 because it will take the previous time step and the gradient at the current time step. So this G sub 2 or G sub 1 or G sub I in general is representing the gradient at a given point. It's not the accumulated gradient. It's a specific gradient at a given point, whereas this V0, V1, V2, V3, these represent the accumulated gradient. So likewise, we can keep on building. We are just going up to 5 steps. We are saying that let's say V5 will be beta times V4 plus 1 minus beta times the gradient squared at the time step 5. Now this V0 would be a value which will be almost equal to 0 because that's where we started. Other than that, if we have to find out V2, we can put the value of V1 here. If you have to find out V3, we can put the value of V2 here from the previous equation, and likewise. So if we do this ourselves up to V5, here is what we're going to get. Now, one important point to observe here is that each squared gradient is getting certain weightage, but the weightage is getting reduced. Why? Because let's say beta was 0.9, then 1 minus beta would be 0.1. That's the weightage that you're giving to the gradient at time step 5. The gradient prior to that, which is represented by G4 or the time step 4, is beta into 1 minus beta. Now, these are both fractions. Beta is 0.9 and 1 minus beta is going to be 0.1. So this is going to be 0.09, which is even less than 0.1. That's what we had here. And further on. So the idea of exponentially weighted moving average is that you give more weightage to the recent observations and the weightage continues to reduce as you keep going in the past. And like I said, this V naught would be almost equal to 0, so this term would not be participating. Now the question comes, what would this look like in case of Adagrad? Because we are essentially trying to improvise Adagrad by bringing the root mean square propagation, right? Let's try to see the equations. So in case of Adagrad, this would simply be a summation of these squared gradients. You don't have these decay factors multiplied to these. Obviously, these decay factors are fractions, so they are reducing the overall value, which means in this equation, we go very aggressive in case of Adagrad because this V5 is much bigger compared to this V5 in case of RMSprop. We don't end up decaying the learning rate to an extent that we stop making progress in a particular direction, at least not so fast as we observed in case of Adagrad. And to visually understand this, you can see this brown line here represents the RMSprop, root mean square propagation, which had a similar start compared to the Adagrad, but it does not really decay or die down before the optimal solution or very close to the optimal solution. It actually almost makes it there. So that's the fundamental difference between the RMSprop and Adagrad. Even RMSprop has a drawback, and let's try to understand that. In fact, that was overcome in another algorithm that's known as the adaptive moment estimation. Let's understand the equations. So Adam essentially puts together the goodness of momentum-based gradient descent as well as the RMSprop. It uses history in both the ways. It uses history to update the average gradient, and it also uses history to update the uncentered variance of gradients, which is pretty much like the RMSprop equation that you saw some time back. So we're giving a certain weightage to the history accumulated till time step t minus 1, and this is all the sum of squared gradients till time step t minus 1. And you're also taking into account the gradient at the time step t squared. That's the RMSprop thing. And this is like momentum. We are giving certain importance to the accumulated history, and we are also giving importance to the most recent gradient, which is what we observe right now. And the decay rates are represented by beta 1 and beta 2 respectively. These are typically set between 0.9 to 0.99. In addition, it performs a bias correction, more to do with the statistical part of it. But you can understand this bias correction ensures that at the initial stages of learning, the gradient stays stable. That's the whole purpose of this. And the parameter update rule, this is interesting. You're seeing the denominator for the learning rate here like the way we had for RMSprop. And you're also seeing this factor here, which is updated just like the way we had in case of momentum. So adaptive moment estimation allows the algorithm to converge to the optimal solution and also executes it faster. So if I were to show that to you, I'll try to draw that manually here. It'll be something like this. So it'll start like this because it is based on momentum, and then it's going to converge towards the center, something like this. But it's based on momentum, so what will happen is that it'll do some oscillations at this stage and finally converge. End of the day, you can see that this kind of achieves both the objectives. Does not die just before the optimal solution, reaches the optimal solution, and also does it faster. Yes, in the process, it may just move a little bit extra and might take some U-turns, but that kind of stays under control. It doesn't continue to update in the direction of the dense features for too long. It kind of optimizes that because of the RMS properties. And it does it faster because of the momentum properties. So I hope this gives you an intuitive understanding of these popular algorithms. Of course, there are many more optimization algorithms that exist, but as a part of deep learning basics, knowing these many would be sufficient. You don't have to memorize the mathematical equations. The idea behind those equations was to make you just familiar with the fact that something like this exists.